and it represents the planar motion of electron. Basically, it represents it in a 2D form. And the probability density function is 0 on the plane where the two lobes touch each other. When the two dumbbells are in between x and y axis, we get dxy orbital. So the distribution of electrons into the orbitals of an atom is called electronic configuration. Hello everyone, this is Ambli Unikrishnan from the Department of Chemistry, Vidhyaashram Pre-University College, the Temple of Excellence, Mysore. So we are back with the last session of the chapter Structure of Atom. So in last session, we discussed about the dual behavior of matter and then Heisenberg's uncertainty principle, which led to the quantum mechanical model of atom, right? We discussed about the important features of the quantum mechanical model of atom, and then we discussed about the 4 quantum numbers, right? So I hope that part is clear. So in this session, we will be discussing about the shapes of the orbitals. Yes, we discussed about orbitals in last session. We will be discussing about the shapes of each of those orbitals, then energies of orbitals. And there are 3 principles or laws which you have to learn. That is AUFBAU's principles, Pauli's exclusion principle, Hund's rule of maximum multiplicity. And finally, we'll be studying on the electronic configuration of atoms. So before moving on to studying about the shapes of different orbitals, I have been using these 2 terms, right? Orbit and orbital frequently. So what exactly is the difference between this orbit and orbital? Or are they the same? Orbit and orbital, are they the same? No, of course they are not the same. So what exactly is the difference between orbit and orbital? Let us see. Okay, so it is a circular path around the nucleus in which the electron revolves, right? In Bohr's model of atom, what did we study? There will be a positively charged nucleus. Yes, and the electrons will be revolving around the nucleus in circular paths which are called as orbits, right? So they are circular paths around the nucleus which the electron revolves. So what about orbital? Yes, it is the region of space, okay? It is a particular region around the nucleus where the probability of finding the electron is maximum. So it is not a perfect circular path, right? It is basically a region where the probability of finding an electron is maximum. So I hope you understood the difference, right? Yes. And it represents the planar motion of electron. Basically, it represents it in a 2D form. Clear? And it represents 3-dimensional motion of electron. It is 3-dimensional. Orbital is 3-dimensional, right? It is basically a region. It is not a circular path. It is not in 2D, it is 3D, right? Orbits are non-directional, hence they cannot explain shape of molecules. So, orbits will not be able to explain the shape of molecules because they are non-directional, right? Now, what about orbitals? Except S orbital, they have directional character. Okay, that means in space, they occupy certain directions. So, if they are having certain directions, that means they can account for the shape of molecules. We will be able to predict the shape of the molecules, which will not be possible in the case of orbits, right? And the maximum number of electrons in an orbit is given by 2n square. Right, in an orbit, a maximum of 2n square electrons can be accommodated. And what did we study about orbital? Yes, in an orbital, a maximum of only 2 electrons are possible, right? An orbital can accommodate a maximum of 2 electrons, and the speciality is that these 2 electrons will be having opposite spin, right? Yes, you remember this. One will be having a clockwise spin and the other one will be having an anti-clockwise spin. So from this, I hope you understood what exactly is the difference between orbit and orbital. So you have to understand it is not the same, right? So that's about orbit and orbital. Now moving on to the topic, shape of S orbital. We are beginning with the shapes of the orbitals. First beginning with the shape of S orbital. Now S orbitals has spherical shape with uniform electron density along all the 3 axes. So as you can see, S orbital is having a spherical shape. Yes, it is having a spherical shape and uniform electron density along all the three axes. So the probability of finding electron along all the three axes will be the same, as it is having a spherical shape or symmetric, we can say. It's symmetric around all the three axes. The probability of finding electron. For 1s orbital, the probability density is maximum and it decreases sharply as we move away from it. So this is 1s orbital that you can see here. Yes, inside, in the center, the nucleus will be present, right? So you can see around the nucleus, there is a very, very dark region, right? So that represents the region where the probability of finding the electron is maximum. So as you can see, for 1s orbital, the probability density is the maximum, right? The dark region is dense in the middle, right? So the probability of finding of electron is maximum there. But as we move far and far away from the nucleus, what happens? You can see the color is getting lighter. That basically means that now as we move away and away from the nucleus, the probability of finding electron becomes lesser. Clear? Now moving on to 2s orbital. The probability density first decreases sharply to 0 and again starts increasing. The region where this probability density function reduces to 0 is called as nodal surface or nodes. Okay, so this is about 1s orbital. Now talking about 2s orbital, what is happening? Yes, the probability density first decreases sharply to 0. So as you can see, the nucleus is present here, and in this area you can see a white region, right? So basically what happens is the electron density comes to 0. So in this area, the white region that you can see, the probability of finding electron will be 0, right? And then suddenly it starts increasing. Again, you can see the black region here after the white region, right? This part. What is happening there? Again, the probability of finding electron increases. So this area, the white region, where the probability of finding electron is 0 is called as nodes. Okay, it is called as nodes, or you can also name it as nodal surfaces. Clear? Yes, so the area in which the probability of finding electron is 0 is called as nodes. And in general, it has been found that ns orbital has n-1 nodes. So what does this mean? Ns orbital has n-1 node. So let us take 1s orbital. How many nodes it will be having? n-1. That means 1 minus 1, which will be 0, right? It is having 0 nodes. Clear? Yes. In the case of 2s orbital, yes, what is happening? n-1 nodes will be there. That means 2 minus 1, that will be equal to 1. Yes, this white region you can see, that is the node. I hope it is clear. For 2s orbital, only one node will be present. So this is the general formula, that is for ns orbital, there will be n-1 nodes. So I hope it is clear. The shape of s orbital, yes, it is having a spherical symmetric shape. I hope it is clear. Now moving on to shape of p orbitals. Unlike s orbital, p orbital consists of two sections called lobes. Okay, that are on either side of the plane that passes through the nucleus. And there are three orbitals in p shell: px, py and pz. Okay, now what about the p subshell did we study? Yes, the L value when it is equal to 1, yes, the corresponding will be p subshell, right? So we know that m can have, if L value is 1, m can have values ranging from minus L to plus L, right? So minus 1, 0 and 1. So as you can see, there will be three orbitals that are possible, right? Yes, so those three orbitals are px, py and pz. Okay, now p orbital has dumbbell shape consisting of two lobes. So what is the shape of p orbital? It is dumbbell shape. Yes, and the probability density function is 0 on the plane where the two lobes touch each other. So what exactly can you understand from this? Let's take this diagram and understand it. Yes, so you can see it is having a dumbbell shape. Yes, two lobes are present on the either side, right? So as you can see in this particular diagram, along the x-axis, the lobe is present or your dumbbell is present. The p orbital is present, right? So this is px. Right, it is along the x-axis. Now moving on to the second one. As you can see, the dumbbell is present along the y-axis. So this is py orbital, right? And in the third one, the dumbbell is present along the z-axis, so that is pz. So this is about the shape of p orbital. So it is having a dumbbell shape, and based on which axis it is present, along which axis it is present, there are three types, that is px, py and pz orbital. So I hope it is clear. And one more point, the probability density function is 0 on the plane where the two lobes touch each other. So this particular point, right, so where the two lobes are touching each other, this plane will not be having, or the probability of finding electron will be 0 there. So basically in this two lobe areas, right, there the probability of finding electron is maximum. But where these two lobes are touching each other, right, as you can see, where it is touching each other, in this case here, in this case here, yes, so that plane will not be having, or the probability of finding electron will be 0 there. So the probability of finding electron will be maximum in the lobes, and where it is touching each other, it will be 0. Yes. So moving on to the next one, shape of d orbitals. So there are 5 orbitals in d subshell. They are dxy, dyz, dzx, dx square minus y square and dz square. Yes, so we know that when L value is equal to 2, yes, then M will be having values ranging from minus L to plus L, right? So minus 2, minus 1, 0, plus 1 and plus 2, right? So yes, you can see 5 orbitals are there, right? So those are dxy, dyz, dzx, dx square minus y square and dz square, and the d orbitals have dumbbell shape. In the case of p orbitals, it is dumbbell shape. In the case of d orbitals, the shape is dumbbell. Okay. Now, first one, the first diagram you can see here. Yes, this is the x-axis, and if this is the y-axis, yes, one dumbbell is present in this direction and another dumbbell is in this direction. Yes, so you can see dumbbell, right? Yeah. And then it is in between the x and y axis. When the two dumbbells are in between x and y axis, we get dxy orbital. Now moving on to dzx. So that means the two dumbbells will be in between z and x axis, right? This is x axis, this is z axis. Then one will be present here, one will be present here, and that is, it is in between x and z axis, which will give you dzx orbital. Now dyz, it will be between y and z axis, that is dyz orbital. Now these two are little different. First one is dx square minus y square orbital. So as you can see, one d orbital, one of the dumbbells is in this direction and one dumbbell is in this direction. So as you can see, it is along x and y axis. One dumbbell is along x axis, one dumbbell is along y axis. Yes, in these three, dxy, dzx and dyz, in these three orbitals, the dumbbells were in between the axis, right? In dx square minus y square, yes, the two dumbbells are along the x and y axis. That is the difference. Now, dz square is having a little bit different shape. One dumbbell is present along the axis and another one dumbbell is present as a circular shape. Okay, around this a circle you can see. So that is about dz square. So these are the 5d orbitals. So I hope it is clear. Now, moving on to the next part, that is radial nodes and angular nodes. So we studied about nodes. What is nodes? It is the region in which the probability of finding electron is 0, right? So there are two types of nodes that you should know, that is radial node and angular node. So first, what is radial nodes? The probability of finding an electron is 0 in a spherical shape. So this radial node is basically, which means that in a sphere or in a spherical shape, where the probability of finding electron is 0, that will be radial nodes. Okay, so what is the difference? Angular nodes, the probability of finding an electron is 0 in a plane. Okay, if the probability of finding an electron is 0 in a plane, it is angular node. If it is 0 in a spherical area or a spherical shape, if the probability of finding electron is 0, then that is radial nodes. So I hope the difference is clear. So how you can find the number of radial nodes? Okay, so in an orbital, how you can find out the number of radial nodes? It is using the equation n minus L minus 1. Okay, so what is n? Principal quantum number. What is L? Azimuthal quantum number. So total number of nodes will be n minus L minus 1. I hope it is clear. Now, angular nodes. The number of angular nodes, how you can find? It is just equal to the azimuthal quantum number. That is, if you know the L value, that will be exactly equal to the number of angular nodes. So, that is clear. Radial nodes is the probability of finding electron is 0 in a spherical shape. And if it is in a plane where the probability of finding electron is 0, that is angular node. Okay, now moving on to the next part, energies of orbitals. So, we studied about orbitals and the different shapes of each of the orbitals, s orbital, p orbital and d orbital. So, now we are going to see the energies associated with these orbitals. So, the energy of an electron in a hydrogen atom, we are considering hydrogen atom, okay, is determined by the principal quantum number. So, using the principal quantum number, the n value, we know what is principal quantum number, we can determine, or the energy of an electron in a hydrogen atom is determined by the principal quantum number. Only by the principal quantum number we will be able to determine the energy in case of hydrogen atom. So, this is the increasing order of energy in case of hydrogen atom. So, 1s orbital will be having less energy than 2s orbital. Okay, and 2s and 2p will be having equal energy. 2s and 2p are having equal energy. Then comes 3s, 3p and 3d which are having the same energy. Then 4s, 4p and 4d and 4f will be having same energy. So, this is in the case of hydrogen atom. Okay, be clear with that. So, this is how it is. Yes, the increasing order of energy. So, in this case, 1s will be having the least energy. Then 2s and 2p. Then 3s, 3p and 3d are having the same energy. Okay. So, the orbitals having same energy are called degenerate orbitals. Okay. So, the orbitals having same amount of energy or same energy are called as degenerate orbital. So, from this what you can say, 2s and 2p will be degenerate. 3s, 3p, 3d will be degenerate. Right. So, the orbitals having same energy are called as degenerate orbitals. So, this is in the case of hydrogen atom. But what happens in the case of other atoms? See, in case of hydrogen, there is a nucleus and only one electron is present. So, only the 1s orbital is coming into existence here. Okay, so the other are actually not needed in this. But what happens in the case of multi-electronic atoms? Yes, in that case, there will be a slight difference in this case. So, that how you can determine the energy for such atoms, we will see that is based on this N plus L rule. Okay, so let's consider the first one, 1s orbital. Okay, we know the N value is 1 and the L value for s orbital is s sub shell is 0, right? So, 1 plus 0 is 1. That is the N plus value. Okay, now moving on to 2s orbital. 2s orbital, yes, that will be 2 plus N plus L value, 2 plus 0, that will be equal to 2. Okay, now let's see for 2p orbital, that will be 2 plus 1, right? That gives you 3. So, from here what you can see, when I added the N plus L value, here I am getting 2 and here I am getting 3. So, what does this N plus L rule say exactly? So, lower the value of N plus L for an orbital, lower its energy. And if the orbitals have same value for N plus L, the orbital having lower value of N will have the lower energy. So, according to the N plus L rule, you can see here 2s orbital is having N plus L value 2. And 2p is having N plus L value 3, right? So, out of which will having more energy? Yes, 2p will be having more energy, no? So, the energy will become 1s, 2s and then 2p, right? Clear? Now, moving on to the next one, 3s. For 3s orbital, yes, N plus L value is 3 plus 0, that is 3. Yes, so now what you can see, 2p and 3s. 2p and 3s, for both of them, the N plus value is same. So, now how do I decide which is having higher energy? Yes, as you can see, N plus L, 2 plus 1 is 3, 3 plus 0 is also 3. So, in both the case, N plus L value is same. So, how do you determine which is having higher and lower energies? Which out of which one is having the highest N value, that will be having more energy. So, the one which is having lower N value, that will be having lower energy. So, out of 2p and 2s, which is having the higher N value, it is 3s, right? So, 3s will be having higher energy. Yes, it is clear. So, then comes 3s. Clear? Now let's consider 3p. For 3p, yes, n plus value is 3 plus 1, right? That is 4. Yes, and then comes 3d. For 3d, n plus value 3 plus, for d it is 2, right? Yes. So it is 5. Okay. So it is clear from there. It is 3s, then comes 3p, then comes 3d. Yes. Now let's see for 4s. Okay. For 4s, what is the n plus L value? It is 4 plus 0. That is 4, right? Now there is a slight problem here. 3d is 5, 4s is 4. And also there is another problem. 3p is also having value 4. So considering 3p and 4s, which will be having higher energy? 4s will be having higher energy, right? Yes. And considering 3d and 4s, which will be having higher energy? Yes, it will be 3d because the value is 5, right? So is this order correct? No. After 3p, what happens? 4s comes and then 3d. Yes. So I hope it is clear. How did I calculate it? Yes, using the n plus L value. So what you have to do is calculate the n plus L value. Whichever is having higher n plus L value will be having higher energy. So like in this case, if both of these are having same values, then whichever is having higher n value will be having higher energy. So I hope it is clear. Yes, now moving on to the two important topics that you need to be knowing, that is effective nuclear charge and shielding effect. Okay. Yes. So what is effective nuclear charge and shielding effect? So effective nuclear charge, which is represented by Z effective. Okay. Z effective. Yes. The net positive charge experienced by the electron from the nucleus. Yes. So what do we know? There is a positively charged nucleus and there is different shells present in which electrons will be present, right? Okay. So in various shells, various number of electrons will be present. Okay. So actually we know that as of now, the model of atom, we know that it is these orbitals, it is 3D, right? So I cannot represent 3D on a board. So that is why, to understand it properly, I am representing it like this. Okay. So a nucleus will be there around which electrons will be present. So what is effective nuclear charge? The net positive charge experienced by the electron from the nucleus. So we know that there is a positively charged nucleus in the center and the electrons are negatively charged. So of course there will be a attraction between each other, right? It is positively charged and negatively charged, right? So this particular positive, yes, the net positive charge experienced by the electron. So the positive charge experienced by the electron, the attraction between them is the effective nuclear charge. So can I say that when more and more protons are present inside, that is when the positive charge keeps on increasing, yes, the effective nuclear charge also increase. More positive charge means more attraction will be there with the nucleus, right? So more positive charge will be experienced by the electron, right? So that is about effective nuclear charge. Now moving on to shielding effect. What is shielding effect? The nuclear force of attraction on the outer electron of the atom is lowered by the electrons present in the inner shell. Hence, the net positive charge experienced by the electron by the nucleus will be lowered. So, what is the sentence? Shielding effect. So, let us consider an atom in which there are, yes, 2 electrons in the first shell. Okay. And considering 1, 2, 3, 4, 5, 6, 7, 8 electrons in the second shell. And there are 4 electrons in the outermost shell. Okay. So, I am considering an atom like this. So, what happens? There is a positively charged nucleus there and there are electrons in different shells. So, this is the outermost shell. So, before the outermost shell, which is the shell present, that is called as penultimate shell. Okay. Penultimate shell. So, the outermost, Yes, the last shell is called as the outermost shell. So in this case, you can see in the penultimate shell, 8 electrons are present. So as we know, we studied in the effective nuclear charge region, we studied that there is a positively charged nucleus and the positive and negative charge attract each other, right? The electrons is negatively charged, so they have an attraction between each other. So what happens? The nucleus attracts the electrons towards it. Yes, so because of these electrons, that is 8 electrons present in the penultimate shell, yes, what happens? The amount of attraction the nucleus is having on the outermost shell will be lowered because of the presence of the electrons in the inner shells. Right, in the first shell there is 2 electrons, in the second shell there are 8 electrons, and in the outermost shell there are 4 electrons, right? Because of the electrons present in the inner shells, what happens? Yes, the nucleus will not be able to attract or have a good contact with the outermost shell, right? So, what happens? The attraction between the nucleus and the outermost shell electrons will decrease. So, that is about shielding effect. So, what is the shielding effect? The inner electrons are shielding the outermost electrons from the nucleus. So, the attraction or the interaction between them will become less. So, the nuclear force of attraction, yes, the force of attraction on the outer electron of the atom, yes, the electrons present on the outermost shell, the force of attraction is lowered by the electrons present in the inner shell. So, because of these electrons, the attraction which is experienced by the outermost shell electrons from the nucleus will be lowered. So, that is shielding effect. I hope it is clear. Yes. Now, moving on to electronic configuration of atoms. So, what is electronic configuration of atoms? You already know how to write the electronic configuration of atoms. We have already studied this in our earlier classes. So, the distribution of electrons into the orbitals of an atom is called electronic configuration. So, how the electrons are being distributed in different orbitals is called as electronic configuration of atoms. So, what you have to understand is electron is filled in the different orbitals in the increasing order of the energies of these orbitals. So, we studied about the energies of orbitals, right? What was the order? 1s, then 2s, then comes 2p, 3s, 3p, then comes 4s, 3d, right? This was the order. So, from this diagram also you can easily understand it. Yes, so as you can see, it is a curved line like this, right? Zigzag line like this. So, it starts from 1s, that is the orbital having least energy. Then comes 2s, then 2p, 3s, then it goes up 3p, 4s, and then comes 3d, 4p, 5s, then 4d, 5p, 6s, and then 4f, 5d, 6p, like that. Energies of the orbitals you can understand from this diagram as well. So, this we already studied, right? Using n plus l values, we were able to calculate the energies of these orbitals. So, this is in the increasing order, right? So, let's take the example of carbon. We know that the atomic number of carbon is 6, right? So, how is the electrons getting filled in this? So, we know that it is in the increasing order of energy of the orbitals, the electrons need to be filled. Yes, so we know that in s orbital, yes, how many electrons can be accommodated? We know that in a single orbital, only 2 electrons can be accommodated, right? So, in 1s, there will be 2 electrons. Yes, that is written as a superscript on top of this. Clear? Now, what happens? Now, how many more electrons are there? 4, right? Total of 6 electrons will be present in carbon. Now, 2s2, right? And in case of 2p, yes, in case of s orbital, we know that only 2 electrons are possible. What about p orbital? P orbital is having total 3 orbitals, right? px, py and pz, right? S is having only 1 orbital, p is having 3 orbitals. Yes, px, py and pz. So, out of the 6 electrons that is possible, yes, each of the orbitals, p is having 3 orbitals, that means a total of 6 electrons can be filled, right? So, out of the 6, 2 will be filled now. So, 2 plus 2 plus 2 will give you 6, that is, yes. Clear? So, this is how you can represent the electronic configuration of carbon. It is 1s2, 2s2, 2p2. Let's take one more example of sodium, which is having an atomic number 11. Okay, so same way in the increasing order of energy, it will be 1s2, yes, then comes 2s2, Then 2p, how many electrons maximum 2p can hold? 6, right? 3 orbitals, 6 electrons. So 2p 6. Now it is 7, 8, 9, 10. We need one more. So that becomes 3s1. Clear? Yes. So 1s2, 2s2, 2p 6 and 3s1. 6 plus 1, 6 plus 2, 7, 8, 9, 10, 11. So yes, sodium. This is the electronic configuration. So this is clear? Yes. So this is one way in which you can represent it. Now you can also represent it in the form of orbital boxes. How is that? Now let's see how to represent carbon in the box form. Okay. So let's consider it. 1s I am drawing. Okay, 1s. We know that 2 electrons are present in 1s and both of them must be having opposite spin. We have already studied this. Now that is how this is represented. One in clockwise direction and one in anti-clockwise direction. Now this is 2s which is having 2 electrons. Yes, so S subshell is having only one orbital, right? So that is why only one box. Now moving on to 2p. Now what about P? We know that there are 3 orbitals in P, right? Px, Py and Pz. Now 2p2. So 1 electron here and 1 electron here. Okay. So now why exactly I have not written the electron here? It is based on a rule. So that we will be studying in the next slide. Okay. Yes. Now let's write about sodium also in the same form. Sodium 1s2. Yes, again it is the same, and 2s2. This is 1s, this is 2s orbital which is having 2 electrons. Now coming to 2p, yes, there are px, py and pz, right? 3 orbitals. So 1 comes here, 2, 3, 4, 5, 6. Okay, 6 is filled. Now there is 3s. 3s is having only 1 electron. So that is represented here. This is 2p and this is 3s. So I hope it is clear in both forms how you can represent it. Yes. So this is based on the increasing order of the energies of these orbitals that you have to fill the electrons. Yes. So now in this case we saw that I have added 1 electron to px, then next one to py. But I have not added the 2 electrons in px itself. So I just told you that it is based on some rules. Okay. So there are 3 rules or principles that you have to study based on which the filling of electrons in different orbitals takes place. Okay. So in any atom, if you take, the electrons must be filled in different orbitals based on these 3 rules that you're going to study. Yes. So the first one is ORBITAL's principle. So what is ORBITAL's principle? In the ground state of atoms, the orbitals are filled in the increasing order of their energies. This one we already discussed, right? Yes. So the orbitals must be filled in the increasing order of their energy. That is, after 1s gets filled, then 2s, then 2p, then 3s, 3p, 4s. Yes, that order should be maintained. Electrons first occupy the lowest energy level and then into higher energy level. So we know that first it will occupy 1s. If 1s gets filled, it moves to 2s, then it moves to 2p, then it moves to 3s and continues. Yes, so this is one thing we already know, that is ORBITAL principle. That is, electrons in the ground state, the atoms, the orbitals are filled in the increasing order of their energies. Okay, so the electrons will be filled inside the orbitals in the increasing order of the energy. Moving on to the next one, that is Pauli's exclusion principle. Now what does this say? According to the principle, no 2 electrons in an atom can have the same set of 4 quantum numbers. So we have studied about quantum numbers, principal quantum number, azimuthal quantum number, magnetic quantum number and spin quantum number. So what does Pauli's exclusion principle say? No 2 electrons can have the same values for all the 4 quantum numbers. At least one quantum number will be different. So what is this? Only 2 electrons may exist in the same orbital and these electrons must have opposite spin. So what are you able to understand from this? So let us see the example here. 1s orbital. Yes, I am considering this particular 1s orbital. So for this electron, I am calculating the quantum numbers. So we know that it is 1s. So n value will be equal to 1. It is s subshell. So L is equal to 0. Yes. So if L is equal to 0, ML will also be equal to 0. And it is in clockwise direction. So S is plus half. Yes. Any doubt? No, right? Now, moving on to this electron, which is present inside the same orbital, 1s. Okay, now calculating the quantum numbers for this. N will be equal to 1, L is equal to 0, ML also will be equal to 0. But what is differing here? S value will be minus half, right? So, see, even these two electrons is present in the same orbital. They are differing in their spin quantum number, right? So, does this apply? Yes. So, in any case, we can say that, yes, no two electrons will be having the same set of 4 quantum numbers. At least the spin quantum number will be different. So, that is what is written here. Only 2 electrons may exist in the same orbital. Yes, we know that in an orbital, maximum of 2 electrons are only possible, and that 2 orbitals will be having opposite spin. So, in this 1s, when we considered the quantum numbers, all the 3 were same, and the 4th one, that is spin quantum number, is changing. One is having clockwise direction and one is having anti-clockwise direction spin. Clear? Yes. So, about this is the 2s orbital the same way. So, as you can see here, in this one, 1s orbital is correct. What about this 2s orbital? Yes, is this representation correct? No, right? Both cannot have same clockwise direction. If one is in this direction, another one must be in this direction, right? So, this representation is not correct. Now, what about this? Yes, in this also both are shown as anti-clockwise direction, right? So, that is not possible. In any orbital, only 2 electrons are possible, right? And those 2 electrons must be having opposite spin. So, that is about Pauli's exclusion principle. Now, moving on to the last rule, that is Hund's rule of maximum multiplicity. It states that pairing of electrons in the orbitals belonging to the same subshell does not take place until each orbital belonging to that subshell is singly occupied. Now, what is this? Let us consider this particular 2p orbital that is represented here. Okay, so we know that in p subshell there are 3 orbitals, right? Yes, this is 2p that I have considered here. Yes, and there are 3 orbitals. We know that. So, in 2p or in p subshell, there are 3 orbitals that are px, py and pz, and we know that all these 3, px, py and pz, all these 3 orbitals are having same energy. Yes, they are degenerate orbitals, right? All these 3 are having same energy. So, in the first case, you can see the first electron I am filling it in here. Okay, so now one more electron comes. Do I fill it here or do I fill it here? Yes, I have to fill it here. Okay, not here. Then again, third electron is coming, I fill it here. Okay, now what I can see in degenerate orbitals, singly the electrons are being occupied. Now, once each orbital is singly occupied, now we will start pairing it. So, now the 4th one will come here, 5th one will come here, 6th one will come here. So, I hope it is clear. Directly, the second electron, if it comes, I cannot fill it in here. It will come in this orbital, then to this orbital, then it starts pairing. Clear? Yes. So, that is what it states. The pairing of electrons in orbitals belonging to same subshell, that means degenerate orbitals, right? Px, Py and Pz, all these 3 are having same energy, and it does not take place until each orbital belonging to that subshell is singly occupied. So, first these 3 singly occupies and then the 4th one will come here. That is what you can see here. So, I hope it is clear. So, what you have to understand, the second one will not directly come here. First, all the 3 has to be singly occupied. So, that is about Hund's rule of maximum multiplicity. Yes, now moving on to the last topic, that is stability of completely and half-filled subshells. So, we understood how we have to, based on the 3 rules, how we can fill the electrons in different orbitals. That is clear. Now, what about half-filled and completely filled subshells? What is that? Let us see. A set of orbitals of same energy is highly stable when all the orbitals are either completely filled or half-filled. So, when an orbital in a subshell, if the orbitals are completely filled or half-filled, they will have some extra stability. We can say that if any substance is having a symmetric shape, we usually say that it is more strong or it has more stability. Yes, symmetric around from all directions. Same way, if the subshell is completely filled or half filled, that is, it is having a symmetry, then they are having some extra stability. Okay, so what is this? Let us take an example and understand. This is chromium. First one is chromium. We know that chromium is having an atomic number of 24. Okay, so we know how to write the electronic configuration of that. It is 1s2, 2s2, 2p6, 3s2, 3p6, 3d4 and 4s1. So according to the increasing order of the energies of orbitals, this is how you represent it. Okay, so I'm considering the last two, that is 3d4. We know d subshell is having 5 orbitals, right? dxy, dyz, dzx, yes. dxy, dyz, dzx, dx square minus y square and dz square. So 3d4 and 4s2. 1, 2, 3, 4. And 4s is present here. This is 3d and this is 4s. 4s is having 2 electrons. Yes. So as you can see here, 4 electrons are filled in the orbitals. Now if I say that from 1 electron from here, if it comes here, 1 more. If it comes here, now can I say that the D subshell is half filled, right? A maximum of 10 electrons can be accommodated in D subshell, right? So now if 1 electron gets transferred from s orbital to d orbital, I'll have 5 electrons here. That is, now it is half filled. So 1 electron moves out from here and it goes there. Right, so an exchange of electrons take place. So actually the electronic configuration that is supposed to be is 3d4 4s2, but because if 1 electron is getting exchanged between 3d5 and 4s2, we get a half filled configuration. This will be the configuration of chromium. That is 1s2, 2s2, 2p6, 3s2, 3p6. 3d5, now it is half filled, and 4s1. So the 1 electron will be transferred to 3d4. So it becomes 3d5, 4s1. Now as it is half filled, it gains extra stability. Yes, now it is symmetric, right? It gains extra stability. One more example for this is copper, which is having an atomic number of 29. Okay, so what is electronic configuration? 1s2, 2s2, 2p6, 3s2, 3p6. 3d9 and 4s2. Now what is 3d9, 4s2? Yes. What is that? 5 orbitals are present in d. 1, 2, 3, 4, 5. So what did we just study? Singly they have to occupy, then we starts pairing, right? So 1, 2, 3, 4, 5, 6, 7, 8 and 9. And then in 4s, 2 electrons are present. Right. So in the same way, if the 3d orbital gets 1 more electron, what happens? It becomes completely filled, right? This is 3d5 in this case. 3d5 it is, right? 5 electrons in each orbital makes it half filled. Now all the 10 electrons will be present here. If 1 electron gets transferred from 4s to 3d, it becomes 3d10. So that will be completely filled. So as I said, when it is completely filled or half filled, it gains extra stability. So this won't be the electronic configuration of copper. This will be the electronic configuration. That it becomes 3d10, 4s1. So I hope it is clear about extra stability of or stability of completely filled and half filled subshells. Because once it is half filled or completely filled, they gain extra stability. So I hope what and all we have discussed in this chapter is clear for you. So we come to an end to the chapter structure of atom. So that's all for today. Thank you.